Hello, welcome to lecture 24 of Elec NH2CI5. In this lecture, I will go over phasors, and phasors are related to the complex forcing functions and the complex response functions we talked about earlier. We obtain them by omitting the e to the j omega t part, and I will show you how we can use them to analyze different circuits. So, as I explained, phasors are effectively the complex for response functions we discussed earlier, but without the e to the j omega t part. For example, if you take a look at this cosine function, this is a cosine in the time domain, but we know from Euler's identity that cosine omega t plus theta v is the real of e to the j omega t plus theta v, because e to the j omega t plus theta v can be written as cosine this angle plus j sine this angle. Now, what we did last time, we said that this whole thing inside the real argument is what we defined as the complex response function or the complex forcing function. Okay, this is what we used last time. This time we're gonna omit the e to the j omega t, and then we say this is our phasor. So the phasor is a complex number. It does not have any dependence on time. This is another thing you must remember. It has an amplitude and it has a phase. Its amplitude is the amplitude of the signal. Its modulus, we can call it modulus for amplitude, is the amplitude of the signal. And its phase is the phase of the signal. Okay? So it tells me, as a complex number, what is the amplitude and the phase of the corresponding sinusoidal signal. But it does not have any information about the frequency of that sinusoidal signal, because e to the j omega t part is missing. So we have to supply for you the e to the j omega t part in order to be able to calculate the actual time domain expression. Okay, so remember, this is what you have to remember about phasors. A phasor is a complex number. It has a magnitude and phase. Its magnitude is the amplitude of the signal. Its phase is the angle of the signal. Okay, and if you want to convert the phasor to the actual signal, you have to multiply by e to the j omega t, and then you take the real part. Okay, so if we know the signal, I can look at the signal immediately and then say the corresponding phasor is AV e to the j theta v without thinking too much about it, because I know that the phasor requires only the amplitude and the phase. And if I have the phasor, I can write the corresponding time domain signal by multiplying by e to the j omega t and then taking the real part. So this slide summarizes really what I said earlier. If you know the phasor, and the phasor are going to use the tilde notation here, then multiplied by e to the j omega t, and then you take the real part. This will give you the corresponding time domain signal. The phasor has all the information we need about the amplitude and the phase, but it does not have any information about the frequency. It does not have any time quantity. It's just a phasor. Okay, just a complex number. The great thing about phasors, and we have seen that even with the complex response functions, is that they transform differential equations into algebraic equations. Because when you differentiate dv by dt, but if you write it as a complex number, the derivative of e to the j omega t will give you j omega e to the j omega t, and the equation becomes an algebraic equation. Okay, so this is the great thing about using phasors, and this is why we're going to use them in analyzing AC circuits. Let's discuss some examples here on the analysis of phasors. We'd like to find the corresponding phasors the phasors corresponding to the three sinusoidal signals. We call these all sinusoidal signals, whether they are cosines or sines. Okay, but we agreed that cosine is our reference. So every signal we're going to be given, we should try to convert it to a cosine to properly determine the phase. Okay, so this one here is 30 cosine 120 pi t plus 120. I can immediately say this is a cosine. The frequency here is 60 hertz because this is omega. Omega is 120 pi. So if you divide it by 2 pi, you get the frequency, so it's 60 hertz. The amplitude is 30. The phase shift is 120. So even without thinking, I can simply say that the phasor is 30 e to the j 120 degrees. This is my corresponding phasor. Okay, I will show you more detailed step in the next slide. Remember that this one and this one, they have first to be converted to a cosine in order to properly determine the phase, because we take the cosine as our reference. So cosine omega t, the signal with zero phase shift. But if it's cosine omega t with plus pi over 2, then it has a phase shift of pi over 2. Let's see how we analyze the first signal. This is the first signal in time. It is 30 cosine 120 pi t plus 120 degrees. But the cosine, as we agreed, is the real of cosine theta is the real of e to the j theta. So I wrote here e to the j theta. And then what I did, I separated the time part, which is e to the j omega t, from the phase part. So this becomes e to the j 120. And this term is what we call the phasor. So this is the phasor of the of a complex of this time domain quantity, and it is 30 e to the j 120 pi and in degrees. So the phase now is written in degrees, or the angle is written in degrees, and I can simply write it, of course, in radian as 2 pi over 3. Another way of writing it is that you can write it this way. You can simply say it is 30 angle 120 degrees, or 30 angle 2 pi over 3. All of them are the same. This is simply saying that this is a complex number whose magnitude is 30 and whose angle is 120 degrees. You can write it in the e to the j theta form, or you can write it this form. Both of them are equivalent, and many books use this one or use that one or use them both. So these are completely equivalent notations to express the same thing. Okay, let's move to the second signal, a 10 sine 60 pi t minus 45 degrees. As I said, a sine signal is a cosine signal that was shifted by 90 degrees in the positive time. So every time I see something like this, sine shifted by 45 degrees is equivalent to cosine shifted by another 90 degrees. So I subtracted 90 degrees from this one. I get minus 135 degrees, which is 3 pi over 4. This term here is 3 pi over 4. Okay, so I can immediately, looking at this one, I could see as a sinusoidal signal whose frequency here, if I divide by 2 pi, will give me 30 hertz, whose amplitude is 10, whose phase is minus 135. So the corresponding phasor is the amplitude e to the minus j, the phase shift or the angle. So 10 e to the minus j 135 degrees. And of course I can simply write it also in polar form as 10 e to the minus j 3 pi over 4. All of them are equivalent. Let's take a look at the last example. Again, this is a sine signal. A sine signal is equal to a cosine signal shifted by another pi over 2. So I subtracted from the existing phase of this one another pi over 2. This term here is 4 pi over 6. This one here is 3 pi over 6. So this will give me pi over 6 net. So this is a cosine signal whose frequency here, if I divide by 2 pi, will give me 90 hertz, whose amplitude is 0.1. This represents a current, so this is 0.1 ampere, and whose phase is pi over 6. So the corresponding phasor is the amplitude multiplying by e to the j pi over 6 here. So this means I can simply also write it in a different form, and this form here is 0.1 angle pi over 6. Or I can simply 0.1 angle 30 degrees. The only thing that I should warn you against here, whether you write it in as pi over 6 or 30 degrees, if you needed to calculate the signal at any time, you must convert this 45 degrees to radian first. The reason is this is omega, radian per second. When you multiply it with time, you get radians. So this is radians. So you cannot add radians to degrees. You have to convert this 45 degrees first to radian, and then you add them together. Okay, let's take one example on how to convert from a phasor to the corresponding time domain signal. So here we are being told that the phasor of the current going through a capacitor is 0.01 angle minus 30 degrees. So it's 0.01 e to the minus j 30 degrees, e to the minus j pi over 6. All of them are the same. And we're told the frequency is 100 Hertz. Would like to calculate the corresponding time domain signal. Remember, a phasor is a complex representation of a real time domain signal. And in order to go from the phasor to the time domain signal, we have to multiply by e to the j omega t, and then we take the real part. So we're going to do that. Remember that omega, this is the frequency in hertz, this f. In order to find omega, you have to multiply by 2 pi first. So this will give you 2 pi multiplied by 100 hertz will give you 200 pi radian per second. So let's put everything together. This is the phasor that we're given. It's 0.01 angle minus 30 degrees. I can write it as 0.01 angle minus pi over 6, or I can write it as 0.01 e to the minus j pi over 6, or 0.01 e to the minus j 30. It doesn't matter. As long as I'm doing things in a consistent way, everything should be fine. Now, if I want to get the time domain signal from the corresponding phasor, this is the phasor, this is the one we have here, you have to multiply by e to the j omega t, and then you take the real part. Remember, omega is equal to 2 pi f, and f is equal to 100 hertz, so this omega will be 200 by t, 200 by, and you multiply by with t, so this omega t 200 by t. So I created this term here. I multiplied my phasor with e to the j omega t, and then I'm going to combine this complex exponent with this complex exponent. This is what I did. I combined them. Now when you take the real part and using the Euler formula, the real part of e to the j theta is cosine theta. So this gives you the real signal. So it's 0.01 cosine 200 by t minus pi over 6. I could have predicted this is going to be the answer from the beginning, because this is the amplitude of my sinusoidal signal, so I can put it here. This is the phase of my sinusoidal signal, so I can put the minus pi over 6 here. And I just need the omega t, and the omega is equal to 200 pi. So I could have predicted this from the very beginning, and this should give me exactly the same answer. Now let's have one example on how to use phasors to analyze circuits. We have done something similar to that before with complex response functions and complex forcing functions. What we're going to be doing here, we'll start first by writing the differential equation governing this circuit, and then we'll replace we will put the complex response function, and then we'll keep only the phasor part, and then we'll try to solve for the phasor, because this is really our target. So I will attempt here to solve for Vc of t, and the Ic of t will become a byproduct of this. Once you know the capacitor voltage, you can get the capacitor current by differentiating it in time and multiplying by C. So this is just a byproduct of the getting the capacitor voltage. Remember, the frequency here is a little bit high. It's 10 to the power 5 hertz. I'm going to solve this problem with this frequency, but I would like you to go back again and solve it with only 100 hertz or 10 hertz. Okay, and see the difference, and see how the value of the capacitor voltage, the amplitude will be completely different. So I'm reminding you of this. I'm using here a little bit high frequency, 10 to the power 5 hertz, 100 kilohertz. I would like you to go back again and repeat this example using only 10 hertz, 100 hertz, 1 kilohertz, and see how the capacitor voltage will become completely different as a result. Okay, we write the differential equation governing this circuit. We have seen something similar to that before. This is the source of voltage here. This is the resistor voltage. This is the capacitor voltage. We have only one loop. Then we apply KVL. We see that Vs of t is equal to VR of t plus Vc of t. And VR of t is equal to the current flowing in the circuit. So there is a current flowing here. This is the capacitor voltage, capacitor current. So this current here is the capacitor current, multiplying the resistance. We have to put everything in complex form. This one here is 3 cosine omega t. So as a phasor, it is 3 angle 0, because we agreed cosine omega t is a signal with a 0 phase. This was our reference. So a 3 angle 0 or 3 e to the j 0. And the corresponding forcing functions is the phasor multiplying by e to the j omega t. What's omega? We're told here in this example that the frequency is 10 to the power 5, then omega is 2 by 10 to the power 5. This is our target. Would like to calculate the phasor of the capacitor voltage. So this is a complex response function of the capacitor voltage. It is a phasor multiplying by e to the j omega t. So as we agreed before, a linear differential equation allows you to use these linear response functions, the complex response functions, and then you solve for the this Vc tilde, and this is really the phasor of the capacitor voltage, and then you have the capacitor voltage in time when you take this back to time by multiplying by e to the j omega t and then taking the real part. Okay, so we put everything together. This is Vs is equal to IR plus Vc, but we write it in terms of complex notations. Vc is now Vc tilde, which is the phasor e to the j omega t. The t here is not showing very well, but this Vc tilde e to the j omega t. This is the corresponding complex response function. Now, this is the capacitor current C dVc by dt. When you differentiate Vc tilde e to the j omega t relative to time, you get j omega Vc tilde e to the j omega t. And I apologize because sometimes I write j as capital J or small j, but both of them are square root of minus 1. Okay? Okay, so we have that. So you simplify things. You multiply C by R by j omega, you get j omega CR. Vc tilde is still there. E to the j omega t will cancel from both sides, and this one reason why we don't need e to the j omega t. Could have directly used the phasors, okay? But remember the derivative, you replace the derivative by j omega, and if you have a second derivative, you replace it by j omega squared. So if this was a differential equation, it became an algebraic equation. There is no derivative anymore. Okay, so we cancel e to the j omega t from both sides, and this is what you end up having. The phasor of the source is equal to the phasor of the capacitor voltage plus j omega CR multiplying the phasor of the capacitor voltage. We take Vc tilde as a common term, the phasor as a common term, so you end up with 1 plus j omega CR. You divide it by the other side, this is what you have. I usually start with notation, with symbols, and then I convert everything at the end to numbers. So omega is 2 pi multiplied the frequency, 10 to the power 5. The capacitor value is 100 microfarads, so it's 10 to the minus 4. The resistance is 10 kilo ohm, 10 to the power 4. This one will cancel with this one. So you obtain this value here for the capacitor phasor. And because the frequency is too high, you can see the imaginary part is way bigger than the real part. This is 10 to the power 5 and this one. So this one is negligible. Relative to this one, I can simply write the expression in this form. Of course, if you want to keep it as it is, please go ahead. But this is 10 to the power 6 almost, and this is 1. So this is negligible relative to this one, and the denominator is effectively a purely imaginary number. So now this is the phasor of the capacitor voltage. If you want the capacitor voltage, the phasor we agreed is a modulus e to the j, the angle. So first we get the modulus. To get the modulus of this term is equal to the modulus of this term. But this modulus is the modulus of the numerator divided by the modulus of the denominator. This is what we have learned from the previous lecture. When you have two complex numbers divided one by the other, then the modulus of the division is the modulus of the numerator divided by the modulus of the denominator. The modulus of 3 is 3. The modulus of this term, this purely imaginary, it is JB. So it's square root of a squared, which is 0, plus b squared, which is this term squared. So it gives you 2 by 10 to the power 5. If you divide them together, you get 4.7 microvolt. You get 4.7 microvolt here. So this is the amplitude of the phasor, or the modulus of the phasor. Now, if you want to get the corresponding angle, we need its angle as well. this phasor is the division of two complex numbers, then its phase will be the phase of the numerator minus the phase of the denominator. We learned this in the previous lecture on complex numbers. So the phase of 3 is 0. The phase of the denominator is the inverse tangent of the imaginary part divided by the real part. I ignored the real part because it is very small, so I made it 0 here. So the inverse tangent of 2 by 10 to the power 5 divided by 0, it's the inverse tangent of infinity. Inverse tangent of infinity is pi over 2. Then the angle of VC tilde, the phasor of the capacitor voltage, will be 0, the angle of the numerator, minus pi over 2. So the last step I did here in this slide, I simply rewrote the capacitor phasor again, and then I said this is a complex number, then its phase is the phase of the numerator minus the phase denominator. Phase of the numerator is 0. Phase of the denominator is the inverse tangent of the imaginary part divided by the real part, but the real part here is 0. So this will give me inverse tangent of infinity, so it's going to give me pi over 2, so this minus pi over 2. So this is really the phasor of the capacitor voltage. I would like you, as I said, to go back again and do these calculations with only 10 and 100 hertz. You notice something very interesting. This amplitude will become bigger, way bigger. And this phase shift will still be negative, but it will be a much smaller angle than pi over 2. So do this, repeat this example for 10 hertz and 100 hertz. Because when you change this frequency, you are changing what we call the impedance of the capacitor. You are making it to get more comparable to the resistance value. So this is the capacitor phasor. So if you want to get the capacitor in time, voltage in time, this is the amplitude. So it's 4.7 microvolt. This is the phase. So it's minus pi over 2, and this is cosine omega t. Omega is 2 pi multiplying by f, which is 10 to the power 5. If you want to get IC of t, what you have to do, you have to differentiate this one relative to time. So this is going to give you minus sine multiplying 2 by 10 to the power 5, and then you multiply the capacitor current. But here it will be extremely small value. Well, it will be in the fraction of a microampere. So you can do that as well. We have done the previous calculations using a differential equation, and then we substituted with the complex response functions, and then we eliminated e to the j omega t, and we kept only the phasor. Now, what if I treat this as a voltage divider? And I'm going to say that the corresponding, we don't call it resistance here in AC, we call it impedance. The corresponding impedance of the capacitor is 1 over j omega c. So I can simply say it this way, that the phasor of the capacitor voltage is equal to the phasor of the source multiplying this impedance by this divided by this impedance over this impedance. The impedance of the resistance is still the value of the resistance. The impedance of the capacitor, as I will prove it to you later, is 1 over j omega c. Now if you do that, you obtain this equation, that the phasor of the capacitor is equal to the phasor of the source divided by 1 plus j omega cr. This is exactly the same equation we got from the differential equation. So if you stop the video at this point and you go back, you see this is exactly what we got. So here we don't really need to worry about using the differential equation anymore, but we just use the equivalent impedance of a capacitor, because the capacitor will introduce a phase shift and will change the amplitude, and both of them are contained in this complex number. Okay, so again, this is exactly the same answer, but it's obtained in a much simpler way, just one line by using it as a voltage divider between two impedances. One of them is 1 over j omega c, the other one is R. It does not change. R is R. The impedance is still the same whether it is AC or DC. Okay, to the last example we're going to discuss in this video. We would like here in this video or this example to use phasor analysis to find I of t. I of t is the current flowing here. I of t is nothing but the capacitor voltage divided by 2K. So I will only worry about the capacitor voltage. And in all the transient examples we discussed, I encourage you as well also to focus on the capacitor voltage or the inductor current, because this is really all what we need. So what I'm going to be doing here, I will write the differential equation governing this circuit, and then I will use the complex response functions, and the term e to the j omega t will cancel out. I will be left only with the phasor of the capacitor voltage, and then I'll solve for that phasor. Then I know the capacitor voltage as a function of time. Once I know the capacitor voltage here with this polarity positive negative, then I know what is the current I of t, because the current I of t flowing here is nothing but the capacitor voltage divided by 2k. Okay, so let's first write that equation. The equation I wrote is that this voltage is equal to this voltage plus this voltage. This voltage here is the capacitor voltage, and this voltage here is the current flowing here multiplying R2. But this current flowing here is the sum of two currents, the capacitor current IC of t plus this current, which is VC divided by R1. Okay, so this is what I did here. So the only trick here is that I'm going to write KVL. I'm going to say that this voltage of the source is equal to this resistor voltage plus this capacitor voltage. This is fine. This capacitor voltage will still be the same, but the voltage here is equal to I multiplying R2. This total current multiplying R2. This total current here is the sum of two currents, this current plus this current. This current here is the capacitor current, and this current here is the capacitor voltage divided by R1, because this voltage is the same as this voltage. So the current here is the capacitor voltage divided by R1. And this is what I wrote here. Okay, and then what I did, I took VC of t as a common term. So I'm left with R2 multiplying IC of t. I replaced IC of t by C dVc by dt. So now I obtain the first order differential equation governing this circuit. Okay, I'm gonna replace this one here by 10 e to the j omega t, e to the j 0, because it has an angle of 0. I will solve for the capacitor voltage. I will replace this one by Vc tilde e to the j omega t, and then I will continue my solution in the same way we did earlier, because we still have a first order differential equation. So this is what I did. I now started using complex response functions, or complex forcing functions. This is the source written as a complex function. It's phasor multiplying e to the j omega t. This is the capacitor voltage written as a complex response function. It's phasor multiplying by e to the j omega t. Now remember, here we had IC of t, but IC of t is C dVc by dt. If you differentiate this phasor relative to time, you get j omega multiplying Vc tilde e to the j omega t, and this is why we got this j omega. So this term here is the current, but the current written in the frequency domain. Okay, so you can see I got rid of the differentiation, and I have now algebraic equation. Get rid of e to the j omega t in both sides, so it's gone. Take Vc tilde, which is the phasor we are looking for, out as a common term. So you obtain 1 plus R2 over R1, and you obtain here j omega R2c. Divide both sides, so you can solve for Vc tilde, which is really our target, the phasor of the capacitor voltage. So you divide the phasor of the source by this term. Okay, and I will show you later how we can obtain this exact expression without having to go through the differential equation. Just remember this expression, we'll get back to it again. Now I finished writing everything in symbols. I'm gonna be substituting. The source is 10 cosine omega t, then as a phasor it's 10 angle 0. R2 is 3 kilo ohm, R1 is 2 kilo ohm, then this term here is 1.5. Omega is 100. Omega is 2 pi multiplying 100, because the frequency is 100, and R2 is given. I substitute for R2, and it's 2k. I substitute for C, is 10 to the minus 5. It's 10 micron. So if you multiply all these quantities together, you obtain 6 pi here. Okay, so we have here 6 pi, and this is really our target. This is this term, so I'm gonna substitute this term here by 6 pi. I'm gonna substitute this one by 1.5. So 1.5 plus 1 will give me 2.5, and I'll write this one as 10 angle 0. Okay, so now this finishes the circuit part. Now just a complex number is equal to a complex number divided by another complex number. But this is a phasor, and the phasor can be written as its modulus e to the g its angle. This is how we write it. I'm looking for the modulus and I'm looking for the angle. To get the modulus, take the modulus of both sides. The modulus of a numerator divided by the denominator is the modulus of the numerator divided by the modulus of the denominator. The modulus of 10 angle 0 is purely real, it's 10. The modulus of the denominator is the square root, the real part squared plus the imaginary part squared. So you get 2.5 squared plus 6 pi squared. And if you do this calculation and you divide by 10, you obtain 0.5261 volt. Now the angle, again we said these are two complex numbers divided. Then the angle of the phasor will be the angle of this division, which is the angle of the numerator minus the angle of the denominator. The angle of the numerator is 0 because it's purely real. The angle of the denominator is the inverse tangent of 6 pi divided by 2.5. The inverse tangent of the imaginary part divided by the real part. This will give you a real answer. It's 82 degrees, but there is a negative sign, so minus 82.44 degrees. So now I know what is Vc of t. It is this term cosine 2 pi ft. F is 100 hertz, remember? And then you subtract from that the angle. Once I know the amplitude, once I know the phase, I know actually the cosine because omega is given. Now if you want to get the current I of t is exactly this Vc of t divided by 2k. So it's Vc of t divided by the resistance 2k because it is in parallel with that resistance. So you simply divide this one by 2k, it will give you a fraction of a milliampere. Now we spent some good time in this expression, this example. We wrote the differential equation, we used the complex response functions, we eliminated the e to the g omega t, we wrote the phasor, we got its modulus, we got its angle, and so on. We could have done the same without having to go through the differential equation at all. So how we do it? You consider this one as an impedance, and then you have two impedances in parallel. We treat them as two resistances in parallel, and I will show you why this is the case later. I'm just jumping ahead a little bit to show you that we can get the same answer in a way easier, in an easier approach. So you have here R1 in parallel with this impedance, which is 1 over j omega c. Then the parallel combination of these two is R1 by 1 over j omega c over R1 plus 1 over j omega c. This is how we did it for resistances, and still applies in the case of impedances. R1, R2 over R1 plus R2. But this is not real anymore. This is an impedance of 1 over j omega c. If you multiply by j omega c numerator and denominator, you obtain 1 plus j omega c R1 and the R1 denominator. So remember, the impedance of these two in parallel, R1 in parallel with this capacitor, is R1 over 1 plus j omega c R1. Now I have a voltage source, I have a 3K in series with this impedance. So remember this 3K in series with this parallel combination, but this is the expression for this parallel combination. So I'm going to be using voltage division. I will try to get the voltage across this parallel combination, and the second part will be the voltage across this resistor. So the voltage across this parallel combination is this parallel resistance, parallel impedance, divided by this parallel impedance plus R2. So this is the parallel impedance here, R1 over 1 plus j omega c R1, and this is a parallel impedance plus R2. This is a voltage division expression, but between this equivalent impedance and this equivalent impedance, and which is equivalent to R2. So if I want to get the voltage here, I multiply this by the phasor of the source. If you simplify this expression and multiply by 1 plus j omega c R, this is what you end up having. If you divide both numerator and denominator by R1, this is what we get at the end. But this is exactly the same expression we got from the differential equation, and I asked you to remember that expression. So what is this telling us? You don't really have to go through the differential equation. replace the capacitor by its corresponding impedance, 1 over j omega c, and later I will show you that the impedance of an inductor is j omega L. Okay, once you have that, you do everything that we have done before. You can apply KCL, you can apply KVL, you can use voltage divider, you can use current divider, but everything will be complex now. All the numbers will be complex. Okay, so I will show you later how this can be done, and I will explain to you why this is the case and how we can get these impedances. Okay, but I'm just looking a little bit ahead to show you that from now on you don't have to write the differential equation at all. You can analyze a circuit with 10 capacitors and 10 inductors with great ease by replacing the capacitor by its impedance 1 over j omega c and replacing the inductor by its impedance j omega L. And then you apply KCL, KVL, voltage division, current division, Thevenin, everything still applies, but all the results will be complex.